All right, let's start by just filling in the vocabulary that we've already sort of been talking about. The essential question for today: what happens when three perpendicular bisectors meet? So we talked about what a perpendicular bisector was. Number one, two lines that intersect at a right angle are perpendicular. We reviewed that. Number two, if a segment is cut into two equal parts at the midpoint, then we would say it has been bisected. Remember, bisect means cut in half. Number three, sort of putting those two things together. If you have something that is perpendicular to a segment and it passes through the midpoint, then it is called a perpendicular bisector. 90 degrees and it cuts in half, it's a perpendicular bisector. Okay, moving on. What's the matter, bro? What's wrong? Okay, here's this theorem. There's really not much to it, but here it is. This theorem is really saying what is kind of going to be obvious to you anyway. Look at segment CP, well, line CP. Let me highlight it. If line CP is the perpendicular bisector, so this yellow thing I just drew, if that is the perpendicular bisector, this theorem is saying that any point on the perpendicular bisector will be equally distant from the endpoints. In other words, the distance from the point to endpoint A will be the same distance to midpoint B.
That's right.
That's pretty close. And that's really just common sense. A perpendicular bisector is going to cut the picture always right down the middle. So it just makes sense that the left side and the right side are going to be the same. You would have guessed that anyway. You didn't really need a theorem for that. But anyway, let's fill in these blanks properly as we go. So that blank right there, equidistant. That word means what it sounds like, equally distant. All right, so I already kind of marked it for you, but CA, the left side of the picture, if this is the perpendicular bisector, should equal, can anybody guess what I'm going to put? Thank you, that just tells me who's paying attention. CA should equal CB. The left side is going to equal the right side. Okay, and then this other so-called theorem is really the same thing, just backwards. It's the converse. The first one said, if you have a perpendicular bisector, then it's going to be equal on both sides. This is saying, look, if you have a point and it's equally distant on both sides, guess what? It must be on the perpendicular bisector. It's really just saying the same thing backwards. It's the converse. So, but if you want to faithfully fill in your little blanks here, all of these blanks are supposed to be filled in with perpendicular bisector. If a point is equidistant, then it's on the perpendicular bisector. So, since in the picture DA equals DB, equally distant, then point D must be on the perpendicular bisector. Just fill that in for me. Here's what it says, and here's why it makes sense. Look at example 1. Look at this diagram. I feel like I should zoom in a little bit. Look at your picture, and we are told that DC is the perpendicular bisector. I'm going to highlight it. This is the perpendicular bisector. Look at the picture and tell me two things that should be congruent to each other in that case. All right, I haven't talked to Gracie yet today. I'm going to try to call as many new people as I can. Give me two things that are congruent, Gracie.
AD and DB.
Okay, AD and DB should be congruent to each other. BAM and BAM. All right, here I've got point D on the perpendicular bisector. If that's true, it should be equidistant. So write this down. So AD should be congruent to DB. Okay, Brian. Let me talk to Brian for a second. There's one other segment that you should be able to tell me two pieces that are equal to each other. Just like follow your common sense and tell me two things that would have to be equal to each other. We are going to know that AE and BE are congruent, but we know that because it's given. See this box I'm drawing? That's given to us already. So give me one other pair other than that, since that's given. Perfect, okay? CA and CB should also be congruent. It can only be a perpendicular bisector if it cuts right through the middle. So CA should equal or be congruent to CB. Okay, simple, simple, simple. Let's see. Chris, Mr. Bautista. I'm looking at B here. Is E on DC? So this is what Brizelda and I were talking about. Is E on DC? Let me zoom in so we can speak more intelligently. Oh, there it is. Okay, Chris. First of all, you understand this, see the arrows? This is a line. So this goes forever in both directions, okay? So this doesn't stop right here. It keeps on going forever. But here's the question. Because of the way that they have not drawn it all the way out, that leaves us with two possibilities. Maybe this line goes out and bam, hits E dead on. Or maybe it goes out and just barely misses it. Comes close, but misses it by a millimeter. We are not going to know which case it is just by looking at it and going, it looks like it's going to hit. We have to use the information that we're given to decide, okay? And here, let me give you this one hint, Chris. See this box up here that of what we were given is what Brian had mentioned at first? Read this box to me. Oh, you're far away. I'll read it to you. You are very far away. AE is congruent to BE. So let's go ahead and mark that on our picture then, okay? AE, 1, 2, 3, is congruent to BE, 1, 2, 3. Now, Chris, that should help us decide if this is a bullseye hitting right on E or if it's going to miss. Can you tell me which it is? It's going to hit it. How do you know? That's correct. How do you know? Right, because they're the same. It's only going to hit it and be on the perpendicular bisector if it's equidistant. So because the distances are the same, sliding back to the actual question, is E on DC? We will say yes. And if I had asked you to explain why, you would have said it's equidistant from the endpoints, or something like that. All right, any questions so far? All right, look at example 2. We are given that EH is the perpendicular bisector. Okay, we're talking about this picture. So once again, I'm going to color it for you. EH is the perpendicular bisector. That's the perpendicular bisector of the picture. Now this is going to be just sort of common sense to you guys. Kayla, let me pick on you for 2 seconds. Look at that picture. Do you see how it's sort of like a kite or something? If this is the perpendicular bisector, the two sides of this kite should be equal to each other. So can you pick one piece and another piece and just name two pieces that should be equal to each other? GD and FG are going to be equal to each other. So let's use that. Okay? Well, for one thing, Those two are just plain marked for us. Okay, so we can just go by the markings. All right, so can everybody agree that GD should equal GF? All right, but let's go ahead and use the expressions. What expressions are sitting right there?
What do you mean?
Right, GD, that's 10y minus 4, right? So 10y minus 4 should equal, what am I about to write, you guys? 7y plus 8. Everybody in this room knows how to solve this equation, am I right?
Yeah.
All right, solve it super fast. I'm going to give you a 5-second head start. All right, so you did minus 7y on both sides, yes? So you got 3y minus 4 is equal to 8. Then you added 4 to both sides like this. You got 3y is equal to 12. You divided by 3, and you got y equals 4. Okay, so we got that by setting this piece equal to this piece. Okay, so far so good. Let's see. Picked on Kayla. You know who I never call on? That guy, and that's why I don't remember your name right now. Tell me your name again. Matt. Matt, tell me another pair of things that would be congruent to each other.
HF and HD.
Let's see. HF and what?
HD.
And HD. Now that's true. But we don't actually have an expression on HD to use. So give me something else.
FE and C.
Yeah, let's go ahead and do FE and DE. All right, let me circle it up for you to make it obvious. Okay, can everybody agree that FE should equal ED? All right, it just follows your common sense. The two halves of the picture. Rodney, what did you get for X, Rodney? I'm assuming you're already done. Oh, but you're not already done. Oh, I'm so disappointed. I need to call on you. It's my fault, Rodney. It's not your fault. I'm slipping. As a teacher, I have let you down.
Oh.
So, Rodney, can you see that these two parts would match?
I see it.
You see it? So what am I about to do with it?
Solve that.
How? What's the equation I'm about to write down?
7x plus 9 equals 9x.
True, true. Right, you set the equation and you solve it. Solve it as fast as you can.
Yeah, fine.
Where do you write this whole stuff?
Yeah, are we not doing anything in example 2?
Oh, yeah, we're just not there yet.
How did we skip that?
10 paciencia.
Wait, what number are we? Or 11? Wait, I'm confused.
We are on problem, we're on example 2. We have not answered a single letter yet. But we need to do what we're doing before we can do that.
X equals 5.
Okay, so you agree with Bree.
They call me that at work, like a cheese.
Like the cheese. That's good stuff. So you guys got 9 equals 2x minus 1. Added 1 to both sides. 10 is equal to 2x. Divided by 2. Yep. Everybody got x equals 5. Okay? Now, everybody has been telling me, but wait, Burton, when are you going to actually answer the questions? I hear you saying that y is 5, and I hear you saying that, x is 5 and y is 4. But that's not what they asked us. They asked us what's EF, DE, and all of this. Anybody know what I'm going to do?
No.
I'm going to plug it in, Cameron says, okay? Look, let's go back to EF, for example. Don't make me break out my highlighter again. Okay? Everybody look at EF. Okay? EF is right here in blue. What's the expression that we have for EF?
7x plus 9.
7x plus 9. So let's use that. EF follow it with me. EF is 7x plus 9.
Are we just gonna plug in X?
Yes, ma'am. So EF is 7x plus 9. But now we know what x is. What was x again, you guys?
5.
X was 5. So that makes 7 times 5 plus 9. So that's 35 plus 9.
Got 44.
That's 44. So EF is 44. Okay, you just plug it in. That's all it is. Scott, look over here every now and then, brother. It makes me nervous when you look straight down the entire time like this, the whole class period. I feel like you're missing something. There's a lot going on the screen. I don't want you to miss it. Okay? Yes, Jamila.
Where'd you get the 5 from?
Here's where I got the 5 from. Let me scroll down. Okay. We got it from this. Would you agree that the 7x plus 9 should equal the 9x minus 1? Okay? Notice how both of these expressions involve x. But if I take those two expressions and set them equal to each other, then I get this. 7x plus 9 equals 9x minus 1. And then I just solved it, and I got x equals 5. That's where I got the x equals 5 from. So right at the beginning of this example, I set these two red pieces equal to each other, and I solved for y. I got 4 for y. And I set these two purple pieces equal to each other, and I solved for x, which turned out to be 5. For the rest of this problem, anytime I see a y, I'm going to plug in 4. Anytime I see an x, I'm going to plug in 5. Does that help? Okay. So we got 44 for EF. Now look, you guys. Fine, I got 44 for EF. When I go to do ED, do I need to do that all over again? Why not? This is 44. So guess what this is going to be?
44.
Right. Shouldn't ED also be 44? Because this is symmetric. If the left side is 44, the right side will also be 44. So I don't need to plug in 5 again. I could. Nothing wrong with it. But it's quicker just to realize, oh, this is 44, this will be 44. So ED should also be 44. So it's quicker if you do that. So DE should be 44. So look, there's one you don't have to show work on. Yay, you guys don't like to show work. Okay, what about FG? What is it? What expression do we have for FG?
7.
Is that the 7y plus 8? Yeah, FG is 7y plus 8. So let's use that. So FG is 7y plus 8. I forgot. What's y again, you guys? 4. So 7 times 4. It turns out to be 36. Why did I write it backwards? I don't know. I do. I'm a little dyslexic, I think. 36. Now, what other side should be 36? And do they ask us for it?
FG.
Okay.
Just kidding.
So this side is 36, which means GD should be 36. Did they ask us for that? Let's see. GD. Yeah, so this one should also be 36. You don't have to do it again. All right, let's see. What about FH? FH. Whoa, that's weird.
3x plus 4.
That's right. Kiara says this one involves both variables. Okay, FH is this guy right here. Do you see it? All right, it's the 3x plus 4y. So let's do that. So we'll do 3x, all right, plus 4y. But x is 5 and y is 4.
15 plus 6.
15 plus 16, what's that?
31.
31. Okay, now be careful. Does that mean the next one's also going to be 31, you guys? No, we have to look at the picture and see what's what. What we found, 31, that was FH. I'm sort of running out of colors. Let me do green. All right, so here's FH in this green color. We just found that this was 31. Okay. Can you see something else that would be 31 that would match it?
HD.
HD would also be 31, wouldn't it? Okay, this would also be 31. Too bad they didn't ask us what HD was. Instead, they asked us what DF is. Can you see what they're asking us for? Do I have any more colors, my friends? They're asking us for this, DF, the purple, all the way across. So how big is that going to be?
62.
That's going to be 62. It's got to be double. Okay, so that one is 62. Why not? I'm going to use this giant marker. 62. Okay, are we done with this side of the page yet?
No.
Dios mío. Vocabulary. When three or more lines, or rays or segments, intersect at the same point, they are called concurrent. Here's an example. See, I just drew 3 lines that all intersect at the same point. The 3 lines I just randomly drew up here, they would be concurrent. All right, so there's an example of concurrent. The point where they all meet is called the point of concurrency. So if this was point P, then in this case, point P would be the point of concurrency. All right, that's just random vocabulary. Now, everything we've done today has been leading us up to this point. This vocabulary word right here, write it down. This is what it's all about. You thought it was all about perpendicular bisector. Really, that was just a stepping stone. Circumcenter. Okay?
Is it like circle?
What did you just say? Alright. Look, here's the key. On the other page, I gave you the vocabulary word circumcenter. Okay? And we just got off track a little bit there. But here's what it is. If we talk about a circle, let me see, can I flip back? No, I cannot flip back successfully. If we talk about a circle, if I said, everybody look at the center of this circle, would we all be looking at the same point?
Yeah. 'Cause there's
Yes,
a
we all know what the center of the circle is. There's only one of them. We would all agree that red dot right here is the center. Okay, we'd all be looking at the same point. Now, on the other hand, triangles have centers too. But, yes, you didn't know this. Okay, this is new information. Triangles have centers similar to the way a circle has a center. But we would not all necessarily agree. If I said everyone point to the center of this triangle, it would depend on how you looked at it, what point you would pick. Depending on how you look at it, there are different names for the triangle center. I'm going to teach you 4 triangle centers. 4. I had to think about it for a second. And here's the first one. The first center of a triangle is called a circumcenter. 3. And here's how it is. One way of thinking of the center of this triangle is to imagine the point that's equally distant from all the corners. Okay? Imagine that, well, that's why I had this picture going. The point of this picture right here is, do you see these red lines? The reason why I drew a circle around it is to emphasize the fact that these are all radii. Does it make sense that these 3 lines would all be the same length? Because they're the radius of the same circle. Okay? But that makes this point the circumcenter. The key thing about a circumcenter is the distance from that center to every corner should be the same. Same to the corners. That's the property of a circumcenter. But you have to understand 2 things. The property is what I just showed you. Equally distant to the vertices, which are the corners. But you also have to know how to build it. Okay? You get it. It's the circumcenter. It'll be equally distant to the corners. But how do you create one? How do you find it in the first place? And that's what I'm going to show you right now. The way that you find that magical circumcenter that's equally distant to the corners is you use the vocabulary word that I spent the first 3/4 of the period talking about. What was that first? Oh, it's still on the board. Ha. What's that vocabulary word we've been talking about?
Perpendicular bisector.
Perpendicular bisector. If you draw me 3 perpendicular bisectors, and you're going to right now, one for every side of this triangle, they should all meet at a certain spot. And guess what? That point where they meet will be the circumcenter, and that point will be equally distant from the corners. Now, let's remember again what a perpendicular bisector was. The name of it pretty much tells you what it is. It's got to be perpendicular, and it's got to bisect, meaning cut in half. So pick a side. I'm going to start with CB. Let me do this. Let's go around and put dots where we think the middle of each side is. For me, I'm thinking the middle seems to be right about there-ish. Okay, if we had more time, we would take out the compasses and the rulers and we would just make this perfect. But we don't have that time today. Maybe tomorrow or the next day. So put 3 dots looking at right about where the midpoints are. So that's the bisector aspect of it. Now let's put 3 segments perpendicular at each spot. So let's see, perpendicular. That means it's, whoa, que pasó? Let me try again. If it's going to be perpendicular, it should make like 90 degrees as best as I can. Okay? On my picture, that's feeling like about 90 degrees to me. Okay, I'm going to put a little box because I'm so happy about it. I'm going to do that 3 times. You do the same thing as me. Try to hit the midpoint. Try to make it perpendicular, 90 degrees. Here I go again. Okay, I'm at the midpoint. I'm shooting for 90 degrees. I think I did an okay job. Maybe not perfect, but good enough for now. All right, I'm going to do that one more time. Other midpoint. Shooting for 90 degrees. If I did it correctly, they should all meet at a common point. That common point where they all met should be the circumcenter. So this red dot, that is the circumcenter of this picture. Okay? Now look, once again, the important thing about that, if I now were to go back and delete all these guidelines that I just drew, if I were to go back and erase all that stuff, does anybody remember the key property of this circumcenter that I just found? What's the property of it? In what sense is this the center of the triangle? It seems to be closer to this side than the other sides. In what universe is this the center of anything? Yes, but I need more. This is the same distance from something. What is it the same distance to? Is it the same distance to the sides? No, it seems like it's closer to this side than the others. What is it the same distance to? It's the same distance to the angles. And that is the key property of the circumcenter. Grant. Wait, you're Grant. Don't pack up early, brother. You weren't here on the first day of class, but the other kids know that's kind of my thing. When kids start getting into backpacks and binders toward the end of class, I kind of freak out.
We only have 2 minutes left.
I know.
Can I talk about it?
All right. These segments that I'm drawing right now, these are the key. This is what makes this the center of the triangle. Because if this is the circumcenter, this and this and this should all be the same. Equidistant to the vertices, the corners.